Alright, so moving along here. In the next slide, I left space, and usually I'd bring up an applet here and show you and demonstrate what it would look like. But instead, what I'm going to do, I'm going to post the website, go to the website, take a look, because you get to play with it a little bit more. What I want to do in here then, don't use the whole space up because you may want to sketch something when it comes to looking at the applet. Um, but just create a nice smooth sinusoidal curve. And for those that haven't taken or got to this point in the grade 11 course, I just want to label a couple of key points here for you. The location of the highest point the graph reaches is what we call a crest. The lowest point in which it reaches, which we'll call trough. Okay. The amplitude is a measurement from the highest to lowest point, or sorry, highest point to the rest line, or rest line to the lowest point. So those would be both amplitude and I'm going to change colors here from start to finish. That would be our period. All right. So a couple of things I want to talk about. Then I want you to try with and you'll see this much better when you try the applet because you can play with it. If we go with high versus low frequency, what would that look like? So maybe we'll just do it like this. High versus low. A high frequency means that a high number of cycles are occurring in that time frame. So a high frequency would look something like that, whereas a low frequency is going to look like that. Less cycles per second. Okay, and if you play with the applet just a little bit, you can see that a little bit more clear. So high frequency, more cycles occur. Low frequency, less cycles occur. The other one is high versus low amplitude. High versus low amplitude. Oops. Low amplitude. So what does that mean? Well, amplitude only affects the size of your crests and troughs. All right, it does not change your period or your cycles, number of cycles. So here would be a high amplitude, and here's a low amplitude, trying to keep the same frequency. All right, so high amplitude versus low amplitude. So it's very important to know the difference between the two and the changes or effects they have on the graph. And like I said, if you go to the applet, you get to play with it and see it a little bit more. You can easily copy and paste it across into your either print it out or you can copy or sketch it. All right. Next I want to talk about is the oscillating spring or the longitudinal vibration. Now, the longitudinal vibration, not overly exciting to be quite honest, because if we put our horizontal displacement here, and that's in meters, and you put your time here in seconds, what results, if we go with the same numbering system, 5, 6, 7, 8 seconds, what happens is you get this, a flat line, because the spring never leaves that natural rest position, so it doesn't have any horizontal displacement. So the result is a straight line. The result graphically is a straight line. All right, well, so how do you do that? How do you graphically represent a longitudinal vibration? Well, quite simply put, again, you can go to your the applet, but what you can do is you can represent it with lines. So let's start off with as the spring gets extended, the part of the metal gets stretched out. So what we do is we spread out and we draw it as vertical lines. As it returns to its natural rest position, the lines get closer and closer together. And then as the spring becomes more and more compressed, the bars get tighter and tighter. As the spring stretches, we start to spread out again, and we repeat the cycle. So this is a very challenging, tedious way to graph it, and not my favorite. So do it as a comparison here, just down below. And this is very important because the terminology is very important. What we would end up with graphically, if we were looking at it or comparing it to a transverse, would be something that looks like this. Okay, so you're making the comparison here. These would line up. So your crest is equal to what we call a compression. And again, you do need to have this terminology known because this is something I'm going to be looking for in your communication skills. So a crest is equal to a compression. So where the bars are tight together, that is what we call a compression. Now where the bars are spread way out, all right, so here and here, that would be similar to the trough, here and here. Then the terminology there is what we call a rarefaction. Okay, so trough is equal to a rarefaction in terms of your longitudinal wave. So very important that you can tell that difference. Okay. I'll do a similar thing that I did with the other graph, and we'll go with high versus low frequency. And if you go to the applet, it's a lot easier to see, better representation of what I can draw. But I'm going to try my best here. So what would it look like? Oops, I don't even need those anymore, do I? So what does a high frequency look like? It means that your bars would stretch and compress more often compared to a low frequency, which would look like a very, very slow progression back together. So compressions and rarefactions occur more often. All right. Now what about high versus low amplitude? Basically, again, it's tough to draw. It's not my favorite one to represent graphically. We don't have to do it very often because the other one is so nice to work with. But if we want a high amplitude, that would mean that the bars are really spread out, and then when they get together, they're really tight. All right. Versus, maybe I should put a divider in there. Okay. So that's a high amplitude or very loud, whereas this one would be not quite as severe. Okay, so I'll just put it tighter together. So anyway, I do encourage you to go to the applet and try it out. Much better representation than what I can draw here. All right, so there we go, and there's the comparison between. You have the terminology and what you need to know right there. So we'll move along. So now we're looking at longitudinal versus transverse. Here's the example. They want you to sketch a wave, amplitude of 10, period of 12. So for the transverse, what we're going to do, we'll just give ourselves XY axes. So we'll go, this is in meters, this is in time in seconds. So amplitude of 10, 12 seconds. So I know that it's going to end at 12 seconds. That means it's halfway through the cycle at 6 seconds. That means that I'm going to have one crest and one trough in there, and they're going to occur in the middle. The nice thing with it, it's nice and symmetrical. And we're going to say that's 10, that's negative 10. So, look like that. Okay, and I'm just doing a rough sketch. So the period, it takes 12 seconds to repeat the cycle. It has a maximum amplitude of 10, and it goes down to -10. So there's the transverse. Now, my point with this example, longitudinal. How do you represent the longitudinal with that information? And it's not easy. It's really, really difficult to actually do it. You can do the period definitely for 12 seconds if you do it in terms of time. So if we had just a x-axis to work from here as such, so 0 to 12 seconds, I could start off with a rare fraction and end with a rare fraction. And in the middle, I would need my compression. The line's going to spread out to that rare fraction. So there's the period, but amplitude is subjective in this case. Okay? Tough to represent. And the reason we like this particular model is because in grade 11, you will be taught and we'll use sine, for example, kx minus p plus q, which allows you to do all the transformations to a sinusoidal graph. So we have a for amplitude. This is what we would call phase shift. And this is still vertical shift. And k is related to your period. All right, and I'll go related to period. So it allows you to incorporate all the information and represent it with an equation, and then you can model and manipulate. So very nice to have it in the transverse. And in fact, what we do is we often take it. The longitudinal is often converted to a transverse graph, because then we can work with it and manipulate it. It still represents the same information, it just looks different. All right, so you want to keep that in mind as we move through. So drawing waves in 2 dimensions. We talked about that, and if you haven't done the investigation, you will have to. For example, if I do a point source, I dip my finger in here, I would draw my waves like this. They would be heading outward. So those would represent the crests or troughs, but more often I have that represent the crests. I'm not going to bother drawing the troughs in because they're in between. And then I just put some directional arrows on to show where the waves are heading. If I have a flat wave heading toward a shoreline, let's say, okay, it's just going to be flat waves. And I'm just going to show that the waves are traveling in that direction. If you're going to draw some curved waves, so kind of look like this. You can show them spreading out, and you can just show some arrows as to the fact that they're heading off in other directions. But basically what we do is we just draw the crests in, and that represents where the waves are actually, and the arrows then show us the direction of travel. So if you haven't done the investigation, that'll be handy. If you've already done the investigation, you probably figured out or have asked how to represent them. So at this point, I'm going to cut off this lesson, and it allows you at this point, you can go and do the investigation, work on it, and then next day finish up the video, then you can do the homework or whatever order you so choose. But there is going to be a part 3 where I do some of the simple math related to period, frequency, and so on and so forth.